Well, hello. In this video, I'm going to show you a problem that's similar to one that you've seen before, but has some important differences. And because of that, we're going to use a different problem-solving procedure than you may have used before. If you're just now getting into the concept of energy, conservation of energy, and related ideas, then you may not have solved problems this way before, but I'll show you that this is a very powerful tool. And let me draw a situation here that shows you why it's so powerful. Imagine we have an object that's going down a ramp. Now, you may have done inclined plane problems before, and you're saying, okay, I've done these before. I've done kinematics. I've done Newton's laws and drawn forces on an object on an inclined plane. But suppose the situation looks like this, where the incline has kind of a funny shape, like that. And we could be starting up at the top here. Let's say we've got a 2 kilogram mass, and something's going to give it an initial push. So we'll call that the initial velocity. And let's use 1.5 meters per second just for a convenient number. Maybe one of the parameters is that the height, the initial height above the ending position, is 0.4 meters. And maybe we're asked about the object when it gets to the end, like what final velocity would it have? So with just the parameters that I've given you here, we can actually solve for this. But you see why you couldn't do this using the traditional dynamics or Newton's laws method. And that's because you couldn't draw a free body diagram that would look the same for the entire trip down this ramp, because the angles are changing, so you've got different inclines, different thetas. You would not have a steady acceleration, so technically you should not be using the kinematics equations that are specifically for uniform acceleration. So in all of those kinds of situations, energy and conservation of energy is probably your best bet to start with. So let me show you how this works. And some of these terms you may have heard before. I'm not going to go into all the detail, but I'm going to show you a problem-solving process. Very similar. If you watched how I solve momentum problems and collision problems, I use a table just to organize all the information. So I'm going to use an energy table here. In some textbooks, you'll see energy bar diagrams used. I'm also going to show you, after I do the table, I'll show you what an equation format looks like, because there's some information in that I think you can't really see in this table. But what's different here with momentum, we talked about multiple objects. Usually it was 2 objects that are colliding. Now we're just talking about the 2 kilogram block. And what we're going to make a table for is its initial energy values and final. And in most problems, there'll be an obvious beginning and an end. And that's what we're referring to here with initial and final. So what are we going to include on our table? Well, this is an energy table. So we're going to look at all the different forms of energy that this object possesses. And again, there's some details here that I'm probably going to gloss over a little bit just to show you what the power of this is without bogging you down with too much detail. So the forms of energy we have in a problem like this are called kinetic. That's associated with the actual motion or speed of the object. And gravitational potential energy. That's associated with some height that the object has compared to another location. So in this problem, I'm going to say at the beginning, it possesses some motion and therefore some kinetic energy. And we calculate that kinetic energy by doing 1/2 mv squared. That's the mass of the object, the speed squared, and then times 1/2. One important and very helpful property of energy is that it is a scalar. It does not have a direction. So with momentum and acceleration and forces, you always had to worry about what direction things were pointing. Well, energy is just something that an object possesses, or a system of object may possess, but it does not have to include any kind of direction. So we can calculate the kinetic energy at the beginning, and at the end, we won't know what it is, but we'll see that we get there. The other type of energy, I'll abbreviate GPE. That stands for gravitational potential energy. And that again is associated with some height that the object is above or below some other height. So we're going to have a comparison. Now in this situation, and we'll learn this about gravitational potential energy, you actually get to choose where you would like to measure heights from. The most convenient height to measure from is typically the lowest point that your object goes in any situation. So in this problem, this is the lowest that it goes here at the end. So I'm going to call that my zero height level. H equals 0 there. And then any other gravitational potential energy is found by doing mgh, where h is the height measured from that particular level. So again, this is the mass of the object. G, I call the strength of the gravitational field. That's why we have gravitational potential energy in these situations. It's because these objects are moving up and down within Earth's gravitational field, and that's what changes the energy. Now, technically, the energy belongs not just to the box, but it belongs to the box and the gravitational field both. But when we do these tables, you can think of it as though it's just a property that the box possesses. Now, in other problems, we're going to have other energy-changing devices. We'll have things like springs, or in electricity and magnetism class, you can have magnetic and electric energy. But in this problem, these are the only two forms we have. So I'm just going to have a row here for the total, and then we'll see how we apply conservation. So kinetic energy, 1/2 mv squared. I did this math earlier. That's 2.25. And the units for energy, the MKS units are joules. It's equivalent to a kilogram meter squared per second squared. So we'll call it 2.25 joules here at the beginning. And then the gravitational potential energy, again, measured from the lowest level, the mass times g, which here is 9.8 newtons per kilogram, times the height of 0.4, gives us 7.84 joules. So if we sum up these energies, we get 10.09 joules of energy. So we would say that's the total energy that the object has up at the top. So here's the power of conservation. As long as there is nothing in this system that would change the energy to some other form other than these two, then we can assume that we're going to get all that energy out at the end. It will just be redistributed. So I said you can't have anything that's going to change it from kinetic and gravitational potential energy into a different form. Well, that would usually be friction. We could also have some other things in there, but if we assume that mu equals 0, that's a pretty big assumption here. We just got a very slippery track. Then that means we have no friction to change any of our energy, and so we can safely apply the conservation of mechanical energy. Again, there are other forms of energy that aren't mechanical that we may have to deal with. If we do have friction, we'll get into that in a subsequent lesson. So the conservation idea, just like we did for the momentum, is that these two quantities will be the same at any position on the ramp. So I could even talk about, how fast it would be going at this position here or up at the top of this hill, but I've just specifically asked for the bottom of the hill. So now we're going to work our way back up. Since we measured gravitational potential energy from this lowest level here, we've essentially defined that level as a 0 gravitational potential energy point, which means all 10.09 joules must now be kinetic. So remember that kinetic energy is 1/2 mv squared. So if 10.09 joules is our 1/2 m times the final velocity squared, again, I'm not going to show every math step, we can now solve for the final velocity. And we will get 3.18 meters per second. I did that calculation earlier. You might show a little bit more algebra than I did there, but that's how we arrive at that final answer. So in the table method, again, it's just a method of organizing your information. These tables will look different if you have springs involved or other forms of energy. But what I want to show you is this same idea of conservation in just an algebraic equation form. So we take the sum of our kinetic and potential energies at the beginning we set them equal to the sum at the end. Well, watch what happens here. This is 1/2 m v initial squared plus mg times the initial height. That's kinetic and potential. And then at the end, we have 1/2 m v final squared plus mgh, where h is the final height. Now in this case, we called our final height 0. It doesn't always have to be that way. Maybe we end up higher, or we just decide to call some other level 0. But here's what I want to get at. Before you start plugging numbers into things, which is really what I did up here in this table, why don't you take a look at some of the relationships here. Notice all of them include mass m. That's the mass of our object. So I would wisely divide out the mass of all of these. And what it leaves us is a simpler form that does not involve any masses. And this form right here, if you perform a little algebra, can be shown to be equivalent to the kinematics equation that we used for uniform acceleration. So it may not be obvious here, but if you apply this relationship, then what you find is you'll get the exact same speed at the bottom of the ramp as what you would get if you just threw this object straight down at this same speed, 1.5 meters per second, and if it fell down straight 0.4 meters, it would also land with this 3.18 meters per second. So whether we have a straight ramp, whether we have kind of a curved ramp like this, or whether we allow it to go straight down, as long as we start at the same height with the same speed, we will always get to the bottom with the same speed. Kind of an interesting idea there. So what we're finding here is really equivalent to what we've done with kinematics and dynamics, just takes on a different kind of language. So I think I'm going to leave it there, and there's certainly more that you'll be able to look at on my videos and maybe some help from your own textbook or your teacher. Thanks for watching. Bye-bye.